So you've got a new big data set, and your fingers are poised above the keyboard, ready to work on your sophisticated analysis and find out what's going on, right? Stop, wait, don't do it. First, eyeball 5 records in that data set, even though there's a trillion of them. And I guarantee you there's a very high chance that you will see something going on in the data that completely surprises you and makes you rethink how you want to do the analysis. Okay, so you've done that, right? You looked at the data, you modified analysis, you did the analysis, and you've seen some great patterns in your data. And now, again, your fingers are over the keyboard, eager to type up an email saying what you've got to start using it, right? Again, stop, wait. Now you know what the most interesting records in that data are. What are the ones that contributed to the results you saw? Eyeball 5 of those records. And again, very high chance you'll see something you totally didn't expect, that the reason for the stuff you saw was not what you expected at all. So, in short, talk to me, eyeball your data early and often. Okay, let me give you a testimonial. 18 months ago, I worked with a summer intern, very bright guy, PhD student at Stanford. And he recently wrote a paper, co-author of a paper, and ignore exactly what it says, except be impressed. But he did a call out to me. He said he'd like to thank me for convincing him of the importance of actually looking at the data. And if you look at this paper, in the introduction they say, you know, we have the best algorithm, the new best algorithm for this problem in genomics. And all previous algorithms came with theoretical guarantees. Ours was the first algorithm to come with a theoretical guarantee and actually work on real data. No one had tried it before. And I have worked since 2000 on various big data sets, right? Gigabyte, terabyte, petabyte data sets in domains from Google, the Google ranking function, automatically organizing documents, and most recently genomics. And what I've seen consistently is that we as programmers are somehow just refuse to look at the actual data when we should. And as a result, we miss stuff that we should be seeing, we waste lots of time, and we just make horrible mistakes. So what I want to do today is talk about, you know, the kinds of things you can spot by just looking at a few data records, and more importantly, what tools you can bring to bear to look at data records to make it actually be a much more fun and profitable experience. Before I do that, I want to go through a couple of distractions from looking at data, things that certainly stop me and other people looking at data. So what's the first thing that we tend to do when given a big data set? And what I'll claim is we adjust knobs, right, rather than look at the data. So the summer intern did this. We had a program, it was making way too many mistakes. And he tuned some knobs, and he got the mistakes down by 5%. And he was really sort of thrilled with this. The problem was our mistake rate was 10 times what it should have been. It's like you're on the Titanic, it's going down, and the purser comes and says, great news, by moving all the deck chairs to the left-hand side, I've reduced the tilt by 1/10 of a degree. You know, there is a time for adjusting parameters, and that time is when you understand what's going on. If you have a basic understanding of what's going on, then go ahead and adjust parameters, and you'll get good results. But if you don't know what's going on, adjusting parameters is basically like debugging your program by making random changes and hoping it works. Right? Not a very good solution. Okay. Second distraction. Looking at data, how boring. And it's not my job, thank God. Well, so let me start with the not my job, because that's actually the answer to the whole thing. Whenever you do analysis of big data, you have in the back of your mind at least some notion of what's going on with that data. And that's going to influence your analysis. Might as well see if there's, you know, some support for that notion before you go and do the analysis. But the more important reason, which I'm actually going to spend a lot of time in this talk on, is that tools will make looking at the data a lot better. Some sort of simple bit of software tooling customized for the data. And even if it's someone else's job to look at the data, it can be your job to help them look at the data, to make looking at the data good. Although in my experience, you know, I use the tools myself, and my reaction when I look at data almost always is that. It's never what I thought. It's never what I imagined. It's just weirder than we can possibly imagine. Okay, let me start with an example from Google. This gentleman is Amit Singhal. For 15 years, he led the ranking algorithm at Google, arguably the world's expert in web ranking. And what would he tell new Google engineers? Look at queries. In other words, look at data, right? Okay, so you're a new Google engineer working on the ranking function, and the world's expert, your boss's boss, a Google fellow tells you should look at queries, look at data, see what's going on. What do? You adjust parameters. That's what we're compelled to do as software engineers for some reason. And I'm completely guilty of this. Now, Google is a very metric-driven company, right? Google has lots of metrics that you can try to tune to make things better. And it would seem off the top of offhand that, well, gee, if I improve revenue, isn't that a good thing? I mean, how can that be a bad idea? Or if I, give users the results they're clicking on, how can that be a bad idea? So the problem is that metrics don't get at the whole story. And if you focus just on the metrics and don't look at the data, you've got problems. So let's go through them one at a time. Revenue, right? Well, it's not the complete story. But actually, things are worse than this. So go back to 2002. At that time, Google and Yahoo were both major players in web search. They had roughly comparable amounts of traffic, believe it or not. Anybody use Yahoo search today? Not only that, they were using equally good search technology because Yahoo got the results from Google. When you did a search on Yahoo, by contract, it went off to the Google search engine. They took the results that Google gave, but they did something different. They took the top results, and they put them over as their own results. But then they put 2 ads in front of them. And they weren't always the best ads. Whereas Google had the ads on the side. Now, if you want to optimize revenue, this is the way to do it, right? Because remember, search engines get paid when you click on ads. They look like regular results. They get way more clicks this way. But if you look at the data, what's going to happen? I'm a user. I click on Buy Australia on eBay. 2 things happen. Yahoo makes money, and next time they're going to try Google, right? So you've optimized short-term revenue, but in the long run, well, you saw what happened. Not a good idea. So you actually have, even if it's something as straightforward as revenue, and Google's CEO famously said, revenue solves all known problems. You have to look at the larger context. The only way to do that is to get away from metric and kind of look at the actual data. A Google ad engineer can actually screw up and make Google millions of dollars too much money. And it's happened. It's sort of hard to write their performance appraisal. Okay. Now, raters. Google actually pays people to look at search results and say, is this good or bad? In some sense, in order to avoid programmers having to look at data, you pay other people to look at the data. And that, that has some advantages, but the raters have their own biases. We all kind of tend to prefer sites we know. They love Wikipedia and things like that. And also, the raters don't really know what the user was thinking. Here's a query, but what was the user actually looking for? And I've spent hours sometimes chasing down queries and looking at the whole context of the previous queries and all that, but what the user was doing. It's a lot of work. Raters don't have time to do that. Okay. Well, what about clicks, right? I mean, the user does a query. They click on the result. That must be what they wanted, right? When I interviewed at Google, they asked me, how would you tell, what good results are? And I said, oh, it's easy. You have users. You see where they're clicking. Well, they hired me anyway. So what's wrong with clicks? Suppose you did a search for Australia, and you're looking for images. And suppose you got this image, or this image, or this image. They're going to get clicks, even though it's not what the user actually intended. And believe me, we've had problems like this. the clicks are not a complete answer. You have to look at, well, what's going on and what's screwing up. You might say, well, okay, for image search, it's not such a problem, but for text, at least the search, clicks should be reliable. But there's also clickbait. Can't guarantee that either. Okay, so basically, if you think of metrics, they're capturing only a piece of the picture, right? You have a forest, and you say a metric, oh, how many trees are in the forest? But this is not what a forest is. This is what a forest is. There's a whole bunch of stuff going on there. And every now and again, you want to go back and look at, ground yourself out in the real world. Don't live just up in the high level of metrics. Okay, so let's look at a tool for looking at queries at Google. The life of a Google ranking engineer is you come up with some idea of new Google, hopefully better Google, usually worse Google, and you compare them. And this tool is called a side-by-side. What you do is you find queries where there's a difference, and it shows here's the results for old Google, here's the results from new Google. It highlights in color the ones that are, the results that are one side, not the other, and it makes them clickable. And if you look at this, you discover there's a small problem. The synonym system has gone crazy and thought that Australia and Austria mean the same thing. If you're at Eva's talk, and she talked about embedding vectors for words, they actually have very similar embedding vectors. It's a plausible mistake to make in some ways. But you can't launch with this kind of an error. Even if your overall metrics say it's a great thing, you can't launch if you're doing this. At least you're going to make it, at least 2 countries people are very unhappy with you. And in fact, what happens when every week there's a meeting at Google to decide what new features get launched. And you look at the metrics, and you also look at example queries. And you've got to be doing well on both of them. Otherwise, you're not going to fire it off. So the example shows 2 key things that you need for eyeballing data. One, you want to select a sample of data to eyeball, and 2, you have to look at it. And they're both absolutely crucial. So that was an example of both of them, right? We selected the ones that mattered the most, the ones where new Google, old Google were different, and we made it easy to tell what the difference was and gave you enough context to see what's happening. Basically, which ones do you eyeball? Well, the ones that matter. And of course, that's going to depend upon what your problem is. And you really want to think about that because it's crucial to get the notion of what matters right in order to eyeball well. So there's a bunch of things that can happen. Right? We saw it by difference. Right? You have 2 different versions of the system and focus on the ones in proportion to how much difference they make. You might do it by volume, right? You might want to say, I want to sample queries in proportion to how often I see that query in the query stream every day. It might be by value, right? I want to sample advertisers by how much money I make from each of those advertisers. Because most of my advertisers don't make very much money before, so I want to sort of sample proportional to that. The original difference sampler was written by Amit. That side-by-side tool was also written by Amit. One thing I found is that experts in fields use visualization. They actually eyeball data, even though they know it, even though Amit can cite queries off the top of his head. If you suggest a ranking change to him, he can tell you, oh, you'll mess up this query. He can always ground out 2 examples. Okay. So there's an interesting thing that happens with weighted examples. Suppose that I want to sample a bunch from Australian companies based on how many employees they have. So I want to do a weighted sample of Australian companies in proportion to how many employees they have. I'm going to do it a slightly funny way. What I'm going to do is pick 4 Australian working stiffs, 4 workers, and then, so each of these people represents roughly 1/4 of all Australian workers, since I've selected 4 uniformly at random. And then I notice what companies they work for. And having done this, I can, of course, kind of forget who the workers are. You can still barely see, right? Yes, good. So the key thing about this is that each of these companies, in terms of the sample, is equally important. right? Even though Rio Tinto has way more workers than the Gantry restaurant. The Gantry restaurant, since it sort of corresponds to Libya, still corresponds to 1/4 of all Australian workers. So when you do one of these weighted samples, it's important to look at each one, because even the ones that by themselves are insignificant are representative of a huge part of the overall population. So, this is telling me that, roughly 1/4 of all Australians work for small companies, right? I could have had a different sample where it looks like, 3/4 of Australians work for small companies. I have no idea which is the actual case. So weighted samples are really nice in that you're not wasting your time eyeballing. Each one of those is equally valuable, equally important. And so you want to do that. Okay. Now, there's a danger in eyeballing, which I want to admit to. Let's suppose that we have some problem cases. And I'm generating problem cases in this case by rolling a 10-sided die and writing down the digit. But we're going to pretend those are problem cases. We don't know it's a completely random process. So here are our problem cases. We're trying to sort of understand what are the issues with the problems. And you look at it and say, I see, wow. It's mostly small numbers, 70% or 4 or less. There's only like 1 9. So maybe our problem is with small numbers. Or you say, well, there's those 4 4s. Maybe our problem is 4s, right? It's really easy to find patterns, even though this is just 10 random numbers. And I've seen this in Google ranking, right? People say, oh, wow, I have a problem with 3-word queries. If I only fix a 3-word query, things would be great. Or, when I have more than 25% prepositions in my document, then I have troubles, right? It's just so easy to spot these things. But let's go with this then. So you say, well, okay, I've got, 4 seem to be a problem. Let me try to suppress 4s and rerun my analysis and see what new problems are. So I rerun the analysis, and I roll the die 10 more times. And look, I've got 2 4s. I made progress. But now it looks like powers of 2 are the problem, right? I've got 4s and 8s and 1s. So I kind of misdiagnosed the first time. My problem is powers of 2. So I'm going to suppress the powers of 2 and rerun the algorithm, meaning roll the die 10 more times. And I swear I did not cheat. These are the next 10 numbers that came up. Look, we've gotten rid of the powers of 2. It's all prime numbers now, right? We've made great progress. Basically, we are evolved to see patterns where there are no patterns there. And it's really easy to understand why, right? If I'm walking along and there's a stick in front of me, I think it's a snake, and I jump aside, right? My friends will laugh at me for sort of jumping aside at a stick. But if I walk along and I step on a snake, I'm less likely to pass my genes on to my descendants. So, the error is much worse for missing something than for seeing something that isn't there. And so, given the alternative, we'll always see something that isn't there, right? You look at this, and it's almost impossible to imagine it's random, right? When in fact, this is what random stuff actually looks like. I may have gotten lucky that last line, but I swear I didn't cheat. So once you eyeball, you then have to do something to make sure that you're not just seeing noise. You can do fancy statistics. You can have a holdout set and relook at the holdout set, depending on what works for you. But you really have to watch for accidental patterns. And I'm guilty of it. At Google, you make your new Google, and then you say, all right, this is my final answer. And then you send that off for a final analysis with new data. And it comes back, and then that's how you verify that it works. But I've said, actually, I have a new final answer. And then I finally went to my final answer, and that one launched. So it doesn't always work well. Okay, let me switch to a new domain, and a case where a programmer did not eyeball the data enough and suffered for it. And I'm not trying to pick on this programmer. This programmer is smart, well-educated, experienced, articulate, handsome. Hey, it's me. So the task was, you've got 100,000 documents or 1 million documents, and you want to organize them. You want to write some code and feed those documents in and organize them into a hierarchy. About 1,000 nodes in the hierarchy, something like that. And I was good, right? I eyeballed the documents first. I eyeballed the hierarchy that came out, because you want to, after analysis as well. And then, being a good software engineer, I made a test. We had a known good hierarchy, and I measured how close my hierarchy was to the good hierarchy. And then, whenever, as the code was evolving, adding new features, whenever I reduced the quality metric, I would basically tune parameters until I got the quality back to what it should be. So, what did I do wrong? Well, I told you, you don't want to be messing with parameters unless you understand what's going on. But I didn't know how the hierarchy had changed when I changed the code. All I knew was my metric had gone down. Well, if my metric goes down, obviously I should fix it, right? So this went on for a year. After a while, I noticed that my metric kept dropping by the same amount. And I'd probably spend a month tuning parameters to get that metric back up to where it was. It was like, 0.5% or something, but I really wanted that 0.5%. So finally, after this year, I said, well, maybe I should look and see what's going on. So I spent an afternoon to write some tooling to do a hierarchy diff to show me what the difference was between the two hierarchies. And here's what I found. Basically, there was one node, and I forget exactly what it was, but in one case, it was saying Catholic, Protestant, other. In another case, it lumped Catholic and Protestant into Christian. Now, okay, wars have been fought over this question. But it's not clear which of these is the better answer. Basically, my metric was just, looking at a distinction that it wasn't clear what was happening. But I had spent so the problem was basically, I hadn't eyeballed it often. That's the key thing. Whenever you see a change, understand what's going on. So this was a sad consequence. Okay. One more example, DNA sequencing. Let me give you an analogy of the DNA sequencing problem. Suppose that someone has been tweeting out the complete works of Shakespeare. And they're doing it not by tweeting the first 140 characters, the next 140 characters. No. They take the complete works, they pick a random spot, and start tweeting at that character, 140 characters. And then they repeat, and they just keep doing this. And they've been doing it so long that they've tweeted every part of it several times by now. And your task is to reassemble the complete works of Shakespeare from all these tweets. Okay? And it turns out that's basically the task of gene assembly. We'll see there's some small differences. So what's happening is you've got, in this case, 2 tweets. And since it's genes, we only have 4 letters to work with. And you notice that, yes, these look like they came from the same section because they have these shared letters. And so we can conclude that, all right, this is a piece of the whole genome. And the whole game is to assemble all these together and reconstruct the whole genome. Now, there are some problems. Let's say this is the correct sequence. Our tweet guy is not very accurate, and he types wrong letters, right? In this case, the gene sequencing data we get has wrong letters in it. Worse, sometimes they leave letters out, or they'll just add an extra letter in. And even worse, they'll do the equivalent of, Romeo, Romeo, wherefore art there something rotten in the state of Denmark? They'll just put 2 random pieces together in one tweet. So we have to deal with these problems. And we have to deal with the fact that the genome is not as pretty as Shakespeare. It's basically a program for building and operating a human. It's been in development for 1 billion years, and it's never had a code review. It's got cut and paste code. It's got commented out code. It's got self-modifying code. Every bad software package you can think of, it's in the genome, and it makes analysis hard. So here was our task. You actually have 2 copies of every piece of DNA, right? One from mommy and one from daddy. It's essentially as if our Twitter guy has 2 copies of the collected works of Shakespeare, which have some differences. And we actually want to understand what are the differences of these 2 copies, what letters are different. Here's a case where, you've got a C from daddy and an A from mommy. And we want to find all these places where these 2 copies of the collected works of Shakespeare are different, given all the other problems going on. And so what's going to happen is if we look at all the tweets that correspond to this, all the sequences we get back, what we're going to see is, we see some C's and we see some A's. So it looks like there's evidence that there's two different versions of that part of the data. And everywhere else they all agree or they have one mistake because these sort of things happen. Okay, so we had written code to do this. And it wasn't working very well. Again, we were in the fortunate case, we had data and we had known the correct answers. Here are all the places where we have variance. So we ran it against the known variance, and it found most of them, but it missed a lot of them, way more than it should have been missing. So what to do? Well, we can put in print statements in our code. We can do tracing. We can tweak some parameters. That's what some intern did. No. Right. Eyeball the data early and often. In this case, often. Right. We now know, we have all this data. We have 100 billion letters, but we know at this spot it's wrong. So let's look at the data at that spot and find out what it's saying. And that we will be able to understand, like, well, what kinds of problems is our program not working with? I had lots of hypotheses of what's going on. Here is, the guy I was working with printed out the data. This is one of those sequences. So basically reading the tweet now top to bottom. And since we want to see context, here's the spot where we expect to see variance. And we're seeing the letters above and after because that can cause various effects. And then here's another sequence of that spot. And there's probably 20 more of these. So did you see the problem? Well, I certainly didn't. In fact, I refused to look at that because I couldn't eyeball it. Right? Your sensory system is way better at spotting patterns than your analytic system. It's basically, don't use a CPU when you've got a GPU that works for the problem. You want to make it so that you're presenting the context and you can do it all in one screenful, in one look, because that's what that's how you can get your sensory processing going. Right? If you have to go back and forth between all the different pages and you're scrolling back and forth, it is going to be boring. It is going to be horrible, right? Okay, so an hour of Python scripting, and now we have each tweet going across horizontally, and here's the column that we're expecting to see the variant in. And we look at it and say, I don't want my program to say there's two versions there. I haven't seen any A's. I see like maybe one mistake. Now, it could be that the problem was we didn't have the A data. For some reason, there's a whole bunch of other tweets that had the A in it, and they didn't get lined up here for some reason. But again, we'd eyeball the data, so we knew we have about the right amount. So that isn't the problem. So we called up the guy who was in a different office about 500 miles away and said, we're sort of confused. We're seeing this data here. Can you explain to us what's going on? And he got back to us a day later and said, oops, sorry, I wrote the data extraction script wrong, and I gave you the wrong data. We could have spent weeks debugging the program. We could have asked him, hey, did you give us the right data? Our program's giving me the right answer. He'd say, yeah, right, sure, it's your fault, obviously. Right. By getting to the data, we had a way to communicate with this guy, right? And we weren't even accusing him of doing something wrong. We never actually thought he made a mistake until he told us that, but it was just like, we don't understand this. So then, okay, we got good data. Our program still had some problems, but by looking at this, we could go through it and find out, and make real progress on fixing our problems. So, in my experience, the data is, okay, almost never what you thought it was, right? That wasn't the first thing I thought. You need to look at it. And I mentioned that, that Amit at Google had this visualization for queries. And again, every expert I've seen has used visualizations. So this is a visualization that Gene Myers uses. He's maybe the world's expert in DNA sequencing. It's called a pile-up diagram. So along the bottom, we have our strand of DNA. And each line represents one of these tweets that's telling us about it. Right, so this one's lining up there. This one's lining up there. And those little diagonals mean that there's some more part of the tweet that didn't line up. It just doesn't match this DNA strand. So, you glance at this and you say, something funny's going on, right? You don't have to know anything about DNA sequencing. You say, I see this sort of non-continuity happening all along there. And also I see twice as many things on the right-hand side as on the left-hand side, roughly. What could be going on? And this is when I said, gene sequence sucks. Well, this is copy and paste code. There's 2 strands of DNA that have a copy and pasted piece of code. So they agree here. And so the guys on the right, half of them are matching the purple strand and half of them are matching the blue strand. And we can't tell the difference. We just sort of line them up on all of them. And then we discovered that, but a bunch of them then were the purple strand. They don't match the rest of the blue strand. So a quick glance and you can find out what's going wrong with your data. Okay. Let me kind of wind up with an example of things going right. This is another ranking change at Google, which I unfortunately can't talk about because it's still proprietary. But typically what happens when you make a change is you discover that you help some queries and you hurt some queries. And the whole game is, well, can I make my change only take effect for the queries I'm going to help and not for the ones I'm going to hurt? And so I had this idea of, for this project we're working on, how to distinguish the queries we'd help from the queries we'd hurt and only have it affect the queries we're going to help. And I implemented it. And I ran the metrics. And yes, 3-to-1, it was distinguishing the winners from the losers. This was going to make us be able to launch the project. But at this time, I've had some experience. It's like, okay, before I announce that we have this answer, let me look at the data. Let me look at the cases where it's saying it's a winner or a loser. And upon looking, my reaction was the usual. It was not doing what I intended at all. It was, however, still doing a good job of distinguishing the winners from the losers. What I had discovered by looking at the data was the best bug of my career. Much better than what I intended to do. And so then by a combination of looking at the data and looking at the code, I figured out what it was doing, implemented a better version of that because the bug wasn't a perfect version of what it was trying to do. And we were able to launch. So to wind up, eyeball the data. Make it so your perceptual system works on it. That avoids boredom. It makes it way better, and it gives you a program, which is, of course, the whole point of the exercise. Eyeball it early before you look at it, before you start doing anything else. And even more crucially, eyeball it often, because as you learn something, at least in my experience, it's never what you thought it was. And if you do that, I think you can actually have fun. Thank you.